Hello everybody, welcome back. So before we get started on the next part of this video, I want to kind of go make a couple announcements from my last video. So the last video I did how to do the repairs on the IF transformers or the IF coils, however you want to pronounce them. And I got quite a few comments on it. And a lot of them had to do with a couple of things where I misspoke. So I want to address that right now. First of all, understand that when I do videos, I do not script them. They are unscripted. A lot of times they're done in what little free time I have, and I just kind of speak off the cuff. And I usually try to catch most of my mistakes. If I make a mistake or say misspeak or something, I usually try to catch that when I edit it. But sometimes those things slip through the cracks and they get out on the video, and by the time I see them on the video, it's really too much of a hassle sometimes to go back, re-edit that part, re-put the thing back together, reprocess the whole series into a video, and then upload it. So unless it's something really, really bad, it might get through. And that's where all of my friends out there come into play. So, the old song, I get by with a little help from my friends. Well, I really do. And I consider a lot of you who are regular watchers of the channel to be friends. And I really appreciate when you come up and kind of catch some of those things. So let's address them. The number one thing that was called out the most was somewhere around 12 or 13 minutes into the video. I was talking about the intermediate frequency transformers, or the IF transformers, and I referred to it as an intermodulation transformer. Yes, you are all 100% correct. That is not the right thing I should have said, and I should have said intermediate frequency. Something I've learned, and that is that from the emails I've been getting lately, I've kind of come to the understanding that some of you, especially those of you who are actually trying to learn this as a hobby or don't have a lot of experience in this, really pay very close attention to my videos, and I'm totally flattered by that. I really appreciate it, and I think that's pretty cool that I can help somebody out. That being said, this is not a professional video. I always list them as entertainment, not education, if you notice, because I feel that if I was going to try to do this as really true education, I would have to spend a lot more time making sure that I don't misspeak or anything like that. So while I hope these videos help all of you, and I hope you can learn some things from them, and I can learn some things from some of you other smarter folks out there that through the comments, understand that sometimes I'm not perfect, and I'm not going to be perfect. But make sure you read the comments, because a lot of the folks that are out there do know what they're doing, and they can help. And some of their comments are very, very helpful, and I'm thankful for all of you who do that. Now, of course, there are always the smarties that come on there and they have to make rude comments, but that's what the delete button's for, and those comments will get deleted. But you know what? Constructive criticism is a good thing. We all learn from it, and we get better from it. So thank you all. The other thing was when we were doing the math formula, when we were calculating what an estimated capacitor value should be for these little IF cans, one of the things I noticed that I did not do, or that you noticed actually, I did mention that when you talk about the capacitor value and when you talk about the inductance value, capacitance is in farads, not microfarads or picofarads, and the inductance is in henries, not millihenries, not microhenries, nothing like that. But what I totally failed on was to say that the frequency has to be in hertz, not megahertz or kilohertz. And sure enough, when I wrote that out, I went back through, somebody mentioned it, and I went and looked at the video. I actually, when I was writing it on the paper, I wrote it as 10.7 instead of 10.7 to the sixth, or whatever the scientific notation should have been. So The best way to deal with that is either to longhand write out the decimal or to write it in scientific notation and keep all of your exponents correct. So thank you again for mentioning that. So once again, to recap, I just wanted you all to know that I appreciate your input. We all learn from one another, and that's what I really think that the internet can be good at. Quite often the internet can be used as a reason to criticize or divide people or whatever, but when people can come together and learn and also enjoy watching something, be entertained, that's really when the internet shines, in my opinion. You know, I talk about Google scholars, people who just Google something and, you know, try to be an authority on things, but you really have to put the time into something to learn it and to get good at it. And things like this, you know, working like this for me and watching these videos together and commenting and exchanging information, that's really how we learn things. So again, thank you all, and now we're going to get started with our next part. So as I said from the last video, the problem we were having was these tubes were running way too hot. And it could be that the actual tube that I chose, I have a couple of those Russian, I think they're called 6P3E or something. They're an equivalent to a 6L6GC type tube, but not exactly. And they do have different bias characteristics as far as the negative voltage you have to put on them to get them to bias properly. So that could be my first problem. I had them, I have a whole bunch of them. I threw them in there to test for test purposes because I didn't want to test this on a good set of original what were they, 6L6WGB 5881 Jan style tubes. These are actually pretty nice tubes and I didn't want to risk them. So it could be a bias problem there. But one of the things that struck me when I looked at the schematic was this, and that is they show this as KT66/EL34. Well, those are very different tubes, and the funny thing is this particular amplifier, which is a later model, it has a serial number, what is it, 42498, so it's a 42,000 series serial number. The other one of these has like a 26,000 series, so they're very far apart in production line, but both of them say that they should have an EL37, and everything I read about these, most of these came with those really excellent EL37 tubes, which are very hard to find now, but they're a very high quality, similar tube to a 6L6. Only very quiet, very good performing, very warm sounding. I guess they're pretty prized by people who are into real audio listening. Anyway, what's wrong with where they say EL34? Well, an EL34 is not a beam tetrode, it is a true pentode tube. And you can look at my Fisher, I think it was the X101C video, and you can see what I'm talking about, the differences between the two. So talking a little bit about these tubes, you kind of have to know the history a little bit. When we deal with Mullard, especially tubes that were developed in this era, there were some patents that were filed about the actual pentode, or this suppressor grid in here. The actual suppressor grid itself was patented, and therefore there were some manufacturers who could not manufacture a true pentode tube without infringing on that patent. So what ended up happening later was other manufacturers got around that by changing that element just slightly. So you notice on this little symbol here, you see these little comma looking things, and they go down and connect directly onto the cathode. those are called your beam element, which it acts exactly just like the pento or the suppressor grid on these Mullard tubes. So the EL34, the EL37 are true pentode tubes where they have an actual grid rather than this beam suppressor. Really, they're just different shaped metal elements that do the same job. They're not really an advantage over one or the other, although there have been many debates over how they make the sound different. Some people say it doesn't make a difference. Other people say it makes a big difference. Regardless, it was a patent that caused it. The other thing is, I have never seen a beam tetrode, as they called it, but it was actually a pentode tube. It had that extra element. I've never seen a beam power tube where the suppressor beam was not internally connected to the cathode. So you only had one pin, just like on a 6L6, you have one pin that's connected both to the G3 as well as the cathode. However, if we go to the original design EL34s, also by Mullard, you can see where you have this same actual grid, just like the EL37. However, pin 8, just like on this, pin 8 goes to the cathode. But see how this one says cathode and G3? This one has cathode here, and G3 is a separate pin, and they're using pin 1. If you look on these ones, which are the same as 6L6s and KT66s and KT88 and 5881s, all those tubes, pin 1, which is right here, is not used. Not used. So, again, here's a 5881, and you look, pin 1, no connection. So, that's really important. Remember, this amp calls for a EL37, even though the schematic says EL34. Why am I saying that's a big deal? Well, if we go over to here, and the other amp I think is the same wiring. They did not change it. Here are your two outputs, and here is pin 1 on this one, and you can see pin 1 is not used. It's empty. There's nothing on it. And you can even, but if you go over to this one, here's pin 1, it has circuitry on it. They're actually using pin 1 of this socket as a tie point. In other words, it's not using it as a connection to the tube itself, but it's using this as a terminal strip. Instead of having to put another terminal strip here, they just use this empty pin. And what they're doing is, here's your 33K resistor coming from your negative bias and going to your 470K resistors that goes down into your bias circuit. So this is just a tie point for your bias. So you look, this one goes to pin 5 of this tube, and this one goes to pin 5 of this tube. Pin 5 is your control grid, and that is your negative bias that biases the tube. So if you were to plug a pair of EL34s into this, even though the schematic calls for it and says it can be in there, you would be connecting, your suppressor grid would not be connected to anything on this tube, and it would be connected to your negative bias voltage on this tube, which would really cause problems. So just an example, you really have to read these schematics and then look at the actual circuit before you just go in and start trying things. You can't just plug a tube in without understanding what it's going to do. Now, the Russian tubes that I have in here now are okay with this, although they have a little bit different bias characteristic from the KT66, the 5881, and some of those, and some of the 6L6s. So I believe that's why this isn't working. Or should I say not working, but why these tubes are running at too high of a dissipation right now. They're not biased properly. So what do we do with this mess? There is, like I said before, there's no adjustment for the bias. And how are they even coming up with the bias? You know, in a normal amplifier, like a guitar amp or something, you would see another little winding that's just above the center tap of the secondary of the power transformer. And it would be like a 50 or 30 volt tap. And you would see a diode put in there reverse, you know, with the arrow pointing towards the coil. And they would put a, you know, capacitor in there between the center tap and the output of that little diode, and you'd make a little negative bias power supply. But if you look here, this is your center tap. Ignore these two windings because these are for a second power string. Let's just look at this main power. When you look at this, here's the center tap, this red and yellow wire, and it doesn't go to ground. It doesn't go to chassis. It goes to what's called a negative 36 volt source. And then you see these weird, you know, there's a capacitor, and then you can see even here, the main filter capacitor, right here, is connected to the center tap, which is not connected to ground. And you look at this even closer, you can see that this, here's the positive of this capacitor. These are electrolytic, so they're polarized. And the negative goes to the center tap, but then you see the negative coming off of the center tap going to the positive, which goes to the chassis. So how on earth are we going to figure this out? Well, using the one-hand rule, you've all heard of the right-hand rule? Well, I'm going to teach you the one-hand rule today. So we're going to troubleshoot this using the one-hand rule. If your finger points at the problem, these two fingers show you some of the possible contributing factors to the problem. This finger points to what's going to solve the problem. And optionally, this one can point to tech support if you need it. I'm messing with you all. So let's redraw the schematic. You know me, any of you that have watched my videos in the past, we redraw the schematic, and that's the main focus of this video. We're going to redraw a schematic and see if it brings to light what's going on. So we have all these weird things, and the first thing you notice is from the center tap, which is supposed to be the common or the ground, you have 3 of the filaments for the tubes, and there is a misprint in these schematics, both in this one and the Sam's PhotoFact. You have V10, V6, and V8, and up here they're not showing it properly, but your V10, V6, and V8 are the 3 12AX7 tubes, and they actually represent the phono stage, the tone control stage, and your pre-driver and phase inverter section. So you're taking all of the audio path preamp tubes, let's say, and you're taking the filaments and somehow running them from the center tap to ground. Well, how does that all work? None of this makes sense, does it? It's confusing. And this is referencing to ground, which is where this is referencing. So are we tying the filaments of this to the cathode of this? I don't know. So what I'm going to do is I'm going to redraw this schematic to put it into better perspective. And that's exactly what I've done. So looking at what they're actually doing. So if this would represent the, I didn't draw the 5V4, but this is what the 5V4 is doing. It is basically just taking, it's a full wave rectifier. And so you have your positive out and your negative. So here's your positive right here, right? And then the negative is going to be the center tap, because both of these plates, the anodes of these, are both connected to either end, and then They go through this tube only in one direction. They'll conduct, right? And refer back to the center tap. So it's just a standard full wave rectifier. So here's your plus and minus from that. And it goes through that 50 ohm 7 watt resistor, and it gets filtered with respect to the center tap. Then it goes through a 100 ohm resistor and goes through a second filter with respect to the center tap. So you have a little pi network, which is to reduce noise. And this is not a really common thing that you see. Normally this would go directly either over here or over here, but they actually have a couple stages of filtering, which there are some arguments on that. This could limit current a little bit, which on the peaks, but since this is only a 30 watt amplifier, this is not going to be much of an influence on that, especially with this capacitor here being 40 microfarads. It'll be just fine. Remember, this is a mono amp and it's only designed for 30 watts, so it should be very clean. It then comes out of the B+. So you see all these, you have these other really high resistance resistors, and these are for high voltage, low current supplies. So there's 340 volts here, but of course it's only 340 volts with very low current. If you put any kind of a load on it, this is going to limit the current, and this voltage will drop very rapidly, and even more so here. So these are really just designed for the preamp stages and so forth. So they're very clean and very quiet voltage sources that cannot produce very high current, or cannot deal with much current. So we're not going to worry about that. However, when we look here, if you redraw this circuit, this is what they're actually doing. And I'll get into these highlighters here in a minute. If you look on the schematic, let's go back to the original. We're just going to go back and forth. These are all in parallel. So you see you have the center tap to the chassis through 100 microfarad. You have the center tap to the chassis through that 400 ohm 5 watt, which, remember, it was wrong. It was 390 ohms at a half watt is what was in there, and it was burned up. And it was reading like 1500 ohms. And then you have the filament string of these three 12AX7s from here to chassis as well. So they're all in parallel. And then the output section here is referencing to the chassis, which would be referencing to this end of these, not to the center tap of the transformer. If you redraw it, this is what you're seeing. So all of the idle current and the operating current of these two vacuum tubes are referencing through this little network of filaments, resistor, and capacitor. So this is actually going to be kind of like a current limiting circuit, number one. It's also going to be a very, very quiet power supply, DC supply, for the filaments. So these filaments are going to run at very, very low noise. And this capacitor is ensuring that. So if there's any kind of ripple due to peaks or any kind of thing when you're driving the amplifier, this capacitor will handle that, and it will ensure that these all stay at 36 volts. It's a voltage divider. So if you put 36 volts across here, so there's a 36 volt drop from here to here. And if you put a 36 volt drop across here, and these are three identical elements, then the voltage will divide equally among the three. So each one will have 12 volts. And a 12AX7 has a 12 volt filament. So this is kind of a rudimentary regulated DC power supply for the filaments. This resistor provides a current divider between these two to ensure that we can carry extra current through here, because remember, these filaments will only limit the current to very low. These are like dim bulbs, right? I keep hitting the camera. So if you put a dim bulb tester in, what does a bulb do? The filament limits the current. Well, these would limit the current to your main output stage. So this is kind of a current bypass for that. So you have a current divider. So your total current is going to be the sum of this current plus this current. So this is very critical to the operation of the amplifier to prevent it from going into clipping and so forth. And all combined, though, this just looks to the circuit like a giant current limiting resistor. So if that's making sense. So the current path, if you're using conventional flow, would be from the positive through these two resistors to the center tap of your output transformer primary, and then splits between the two vacuum tubes, the two 5881s or whatever they're going to be, through the cathodes, correct? And we're not talking about biasing yet. And then return path through this current limiting to your center tap of your power transformer right here. So again, the current path would be out of here, right, into here, through these cathodes, up into here, and then back to here. And there you go. That's your current path. Where it gets interesting is if you measure the difference between here and here, there's a 36 volt drop, provided that you have the correct idle currents and everything in this loop. So this loop, this is kind of like a regulated circuit in some ways, but in other ways it is not. It depends on the voltage up here. It depends on how hard these tubes here are turned on. So it's kind of self-regulating. It's a very unique circuit. I've never seen anything configured like this before. And if you remember on the X101C video, it wasn't this same layout, but they did another thing where they would take this filament string of the original, your AF stage, your preamps, and they put them in line with the cathodes in a similar manner. So you can see this is where they started this kind of thought process. And then later on in their later stereo amplifiers, they carried it over and kind of perfected it. The difference is the later models had adjustable bias. This one has pretty much a fixed bias. You can't adjust it. These are fixed value resistors in here. It is what it is. So there is a voltage drop between here and here, and I think it's probably, by the schematics, it's probably about a 1 volt difference. And when you add that 1 volt to the 36 volts, they're showing it as a negative or a minus 37 volt bias at pin 5. So it's negative 37 volts, even though this is negative 36 volts here. And what I'm getting on this when I test it is not that. Instead of getting the 37 volts, it's actually lower than 36. It's coming out to 34 or something like that, 35, somewhere around there. And that's because the tubes that I'm using now don't work with this formula as intended. So we may have to, if we want to use them, we may have to play with this, or we have to go to the original tubes that belong in here, which is probably what I'm going to do. Here's where it gets interesting. Conventional flow, we said, right? So here's the current path, as we talked about, right? Here's your loop, right? But remember, you're using conventional flow, the positive always flows towards the negative, okay? And we won't get into conventional flow versus electron flow. That's another video maybe. So if that's the case here, this is more negative than this. So what is going to happen in this instance is when it comes to the bias circuit, current is going to flow in the opposite direction. So it's going to go through here and because it's negative voltages we're dealing with, right? So it's going to go through here, up through this resistor network, and down here, and return down to here. So check this out. Opposite current paths using the same wire path. Pretty cool, huh? It's all a matter of reference. But that's how this works. So now that we drew this out, it's much clearer to look at, and you can at least see what they were thinking when they did this. And then of course you have these 68 ohm resistors, which are your screen grid droppers. So you're going to have your B plus going through these 68 ohms into your pin 4s, which is the screen grid. And then there's your suppressor grid at the top. And I didn't draw it in because I didn't have room to draw it, but these internally are connected to the cathode. So that one there and this one down here. So now that we know that, we can get in there and take some measurements, and hopefully we can see exactly what it is this thing's doing, and then we can maybe take some measurements at what the idle currents are with these Russian 6L6 type tubes. So first thing I'm going to do is take a bunch of voltage measurements and write them down, and then we're just going to see what we can do with all these numbers that we get. And the first voltage I'm going to measure is the voltage drop between your center tap of your output transformer to either side of these. And I'm also going to measure the resistance of each coil. Now the schematic mentions what those resistances should be on the transformer, at least used in this version of this amp. And they're saying that one side is 130 ohms and the other side is 140 ohms. And yes, quite often they have a slight resistance difference in the windings. And that's normal. That's the way they design it. I believe some of this is because when you start, as you wind these coils on top of one another, each layer of windings wraps around the top of the previous layer, which changes the diameter of each winding. So as you go further out, those windings, the turns ratio is the same, but the actual amount or length of wire increases as you get bigger and bigger in diameter. Think of a snowball, you know, it's a snowball effect. As you roll the snowball downhill and it picks up more snow, it gets bigger in diameter. So what that ends up meaning is that the inside part of the coil is going to be a little bit lower resistance than the outside part of the coil. But the turns ratio between, you know, here and here and here and here is going to be the same. This would be the same amount of turns. Interesting. So number one, if I go over to ohms and I measure this first tube, it's reading about 119.3, it kind of bounces around, 119 ohms. And if I look at the center tap to the other side, if you notice, it is higher. It's 147.6 or 7. And it'll change a little bit with the probes, but close enough. So we're going to write those numbers down. Now, leaving the probes in the same place, I've now just switched over to voltage instead of resistance. We're going to measure voltage. And we're going to look at the actual voltage across that coil. So we're looking at our actual voltage drop across here. Okay, so there we go. Let's turn it on and let's see what happens. Takes it a second to warm up. And you can see after everything warms up and kind of regulates. And did you notice that it was higher and then it dropped again? And that's the influence of those 12AX7s coming into there and changing the bias as they regulate. So we have about 8.6 volts. So we're going to write that down. I've now moved my probes onto the screen grid, which is pin 4. And to pin 3 right here. And don't pay attention to these voltages right now. That's not what we're measuring. Those are with reference to ground. So we're going to measure the voltage drop between the anode and the screen grid. And when we look at it, that voltage drop is about 8.2 volts. So we're going to write that down now. The next thing I'm going to look at is the voltage from the anode to the cathode. And in this case, since this is a fixed bias design, cathode and chassis ground are tied together. So I could connect to the chassis, but I'm on pin 8, which is the cathode, and we can see the voltage across the tube from anode cathode. So our anode cathode voltage is 393.6 volts. And if I go from the screen to the cathode, it's 401.5 volts. So the screen grid is higher voltage with respect to cathode than the plate or the anode. Why is that? Let's look. When we look at this from a DC standpoint, if you notice, here's your incoming voltage, and they're both referencing through the tube to ground or to chassis. But this side goes through a 68 ohm resistor. This side goes through a 130 ohm resistor. So that's exactly why, since there's a different DC resistance, this has higher resistance, this is going to be a little bit lower voltage. And again, that's the function of the screen grid, and we could get more into that in another video once again. But anyway, that's where we are. Now we have our numbers. Let's do a little bit of calculating. So looking at the math, we can see our problem. If current equals voltage divided by resistance, if we take that voltage drop across the winding, which is 8.6 volts on V11, divide it by the 119.4 ohms, we get 0.072 amps, or 72 milliamps. And if we take and look at, and I know we could jump through this and there's a power formula for this, but we're working through it, through the numbers so we can see. Power equals the current times the voltage, and that's going to be your 72 milliamps times your 393.6 volts, because that's the voltage from the anode to the cathode. So if we measure anode to cathode, remember it was 393.6. So we take the anode cathode voltage times the plate current, and we get 28 watts. Now, if we wanted to get more accurate, we could take our measurements from our screen grid and we would calculate the screen current as well, which is going to be very, very low. And it's only going to be maybe a couple of milliamps, which you could subtract from it, but really isn't going to make, in a Class AB amp like this, is not going to make a big enough difference to worry about it. So we're just going to use this. So this tube is dissipating 28 watts at idle. If we go to V12, and we remember we talked about that the resistance is a little bit higher on that winding, we naturally are going to have a little bit higher voltage drop. It's 11.5. Divide it by the 147.8 ohms. You're going to get about 0.078 or 78 milliamps. Take that times the voltage, which was 393.6, or actually measuring it on that tube was 396.4. It was a little bit different. You're sitting at about 30.9 watts. So they're not really terribly far apart as far as matching is concerned, but they are both grossly too high. Why do I say that? So if we look at a 6L6GC, which is a pretty powerful output tube, and you look at the design maximum ratings, the maximum plate dissipation on that would be 30 watts when we're in pentode connection, which we are. So right there, it's already at its maximum. But if we go and look at the Russian tube, remember they're a little bit different and their biasing is different. The 6P3S or SE, if we look at the maximum anode dissipation there, it's only 20 watts. So we're exceeding, by a large margin, we're exceeding the idle current of those tubes. So our choice is to swap out the tube for the correct one or to modify the bias circuit, which on this is not going to be the easiest thing on earth, although we could play around with that 33K resistor and a few other things that we could do to change that. But because of how they're all intertwined in this schematic, I would rather have the correct tube. So this is not one of those amps you're going to do tube rolling in. You're not going to just swap in a whole bunch of different tubes without changing something in the circuit. So there it is. Let's see with the 5881s in there if any of this is going to change. So running the numbers with the 5881s really didn't yield much difference. It's still running way too high. It's maybe 1 watt less or so. So really what that's telling us is that we need to reset the bias on this. So looking at the schematic, you can kind of start to see the inherent flaw with this design. Because this is a fixed voltage drop, the most bias voltage you could ever get is 36 volts. That's what it is. And of course, by messing around with this value here, you can get this to go up, but what's going to happen is your voltage drop across here is going to be higher than 36 volts, which is going to put more voltage across the filaments than you should have. And that's, of course, not a good thing either. We don't want our filaments to run too hot. So what are we going to do about it? The problem is this design is very specific to the type of vacuum tube that you're going to use on the outputs. And if you remember, this one was set up for EL37s. Now, depending on the mutual conductance and many other factors in the individual tube type, the bias voltage that you're going to need is going to be different based upon the type of tube you're using. In other words, one tube may work at negative 36 volts when you have 400 volts at the plate, but it may not. It may need a different bias voltage if you change to a different tube type. So what we need to do is, there's a couple of options. The first option would be we could come off of the transformer in a more traditional manner, like here, and we can put a diode in here, a reverse bias diode, and you can make a negative voltage, separate negative voltage bias supply, and we can even put a pot on it and make it adjustable. The problem is you can't just put a separate bias circuit in here. Because all of these things are dependent upon one another, as you adjust the bias here, you may get the idle current correctly set here. However, it's going to affect the voltage drop over here. In other words, these two things interact with one another. So that's why this, when it's set up properly, is kind of a self-regulating circuit. And in a way, this thing is somewhat cathode biased, because you look, the cathode, they're showing this ground point here, but really the return path is through this network and back to the transformer. So in a way, this is in line with your cathode, so it is somewhat cathode biased. And then this negative voltage is kind of a feedback for it in some sort of way. And it all works as long as this tube has the proper curves as to how it reacts to those voltages and currents. So what can we do? I mean, the way they had this thing biased, it worked, but it was way too high. And this thing is not running in triode mode, it's running in pentode mode, meaning there's a voltage difference. There's a higher voltage on your screen grid than there is on your anode. And when you do that, this thing's going to run really hot if you don't have enough bias on here. You need a really high bias voltage. In other words, like a 6L6GC, if you look at common guitar amplifiers, you know, like a Fender guitar amp or something like that, you look at the way some of those are biased, your bias voltages are always 40, 50 volts or more, depending on the voltage going in. The other thing is this power supply, even though it says 420 volts, it can go way, way higher than that. Remember, this thing is 1956, what, 56, 57, something around there. And at that time, the mains voltage for the United States was much lower. It was anywhere from 110 to 117 volts. We're now seeing closer to 120 to 125 volts. And if this thing is, let's say, 3 to 1, so meaning for every 1 volt you put into the power transformer, you get 3 volts out. For every 1 volt higher than its rated voltage that you put into at the mains, that's 3 more volts higher it's going to be here. So an extra 7 or 8 volts can amount to quite a bit. You can get anywhere 20 to 25 volts, somewhere around there, of higher B+. That's going to change this because, once again, if you check your idle current, that idle current at a higher voltage is a higher plate dissipation. So everything's interactive on these. So what do we need to do? Well, first thing I don't like is I don't like the fact that this voltage can vary across these filaments. We can change this voltage just by changing the way these tubes are biased. And we can either make the voltage lower than it needs to be or higher than it needs to be. And it's okay if your filament voltage is a little bit low. You can go a little bit low on the filaments. It'll actually make the tube a little bit quieter. It'll also make it a little bit less sensitive. And that might be good. However, if you go the opposite direction and you run the tube hot, it's going to start to get noisy and it's going to reduce the life expectancy of the tube. So we have to come up with a way to fix it. So how are we going to do that? I wondered why I had this paper here, didn't you? So here's what I came up with. So you can see what we've done. We've added a little bit of circuitry here. So the first thing I've done is I put a series of Zener diodes across the filament string. And if you notice, there's a 12 volt, a 13 volt, and a 12 volt. And these are 1 watt Zeners. And remember, we're not going to go that much over, so these aren't going to have to clip or dissipate very much energy. So a 1 watt Zener will be just fine. So 12, 13, and 12. So at 37 volts roughly, this will start to clamp the voltage off here. So it can never get above what these filaments can run at. In addition to that, these tubes were running way too hot. We should only have about 17 watts of idle current for class AB, especially when it's running in pentode mode. So 17 watts on a 6L6GC is somewhere around that 70% range. You can go a little above that, 18, 19 watts. You don't want to go much above that though. And this thing was idling at 27 to 29 watts, as high as 31 watts at some points in time. And that's what was causing the tubes to go red plate every now and then. They wouldn't go grossly red plating, but if you turn the lights off, you can see the seams on the corner of the tube would start to glow and get orange. That's not good. So what we're going to do is we're going to, first of all, limit this voltage here. That means that if we need more than 36 volts for our bias, which we do, we need closer to in the 40 range, over 40 volts, this is never going to work. So what I did was I raised this by putting a 5 watt 6.3 volt Zener diode in series. So if you look up here a little bit, I'll move the camera up just a hair. Here we go. Right about here is where you would see that Zener diode there. Now, by putting this in like this, it caused the circuit to drive way down. So now we only had maybe about a 30 volt drop here instead of a 36 volt, meaning that that shunt resistor that's in parallel with the filaments was too low, and therefore we had to increase that value, and that value ended up being 2.4K, was right where we needed to be. So with this circuit, the amplifier idles right where you want it, and I have to admit, it's probably one of the best sounding vacuum tube amplifiers I've ever heard of this vintage. This thing, now not talking the tone control section or anything like that, but just the sound of it it's astounding. I never thought it would perform like this. So let's take a look at what we have. And here's our circuit mod. So over in this area here underneath, there used to be a 33K resistor, and it would take that bias voltage at this point, because that's where that is. In other words, this point right here on this vacuum tube is this point right here, okay? And this point right here is this point down here. So I removed that resistor going from there to this center point. And this is where your bias goes into the two outputs. I'm off camera, ain't I? Okay, here we go. So we're up here. And I removed that resistor going from there to there. And I put a wire in there, and you can see that orange wire. It goes down, and it comes down to right here. And there's your 33K resistor relocated down here. I added another little terminal strip next to this one. Our Zener diode network is then wired onto this. And you can see down here, I just came out of there, and there's this little jumper wire that goes over to here. And where that 400 ohm resistor used to be, we now have our 2.4K, and it's on really, really stiff, solid copper. So it can't move. And it's a 20 watt resistor. It didn't need to be that high, but that's the only one I had in that value. And to be honest, it's actually an advantage because it hardly even gets warm to the touch at all. Everything runs cool. That's another thing that's important to me. I want things to last a long time. I don't want all these components to run at really high heat. So if you notice, this 100 ohm resistor now is a chassis mounted one, and the 50 ohm over here is a chassis mounted one. So everything's going to run nice and cool, and after long periods of listening at high volumes, nothing changes, nothing gets hot. It's really, really stable. So let's connect a couple of meters to this, and let's look at some of the voltages now. Okay, I hope we got everything in view here and we can see everything. Some of it on a little screen, this is going to look really tiny for you guys, but it's the only way I could get everything in shot. The meter up here on the bench, that is going to be your B+ with respect to the cathode of the output tubes. So that bench meter is reading from here on the anode, your B+ through here into the anode. So we're measuring from anode to cathode. That's what I should have said. So that's your anode to cathode voltage. That's going to be your high voltage B+. This meter, the fluke meter, right here, this is measuring the voltage drop across the output transformer from here to here. This is what we're going to use to calculate our idle current for this particular tube right here. And this meter right here is reading the voltage drop across the string here, the filament string, and we can move that over to here to measure the total bias voltage. But we should see our 36 volts right here, our negative 36 volts, if everything is correct. So everything's plugged in. Let's turn the power on, and we'll watch everything hopefully stabilize. And the first thing you'll notice, and you can see this is coming up, and it takes its good old time. And those are the filaments warming up on those three 12AX7 tubes. You can see anode to cathode, we have 427 volts. And of course, Tony is reading the wrong voltage here. Let's get on the right test point. There we go. So we have 5.8 volts on the transformer. So the winding of that transformer, just so you know, right up here from pin 3 to the center tap is 119.4 ohms. So if we want to look at the current, current equals voltage divided by resistance. So if we take 5.8 volts, don't worry about the negative, divided by 119.4, that equals about 48 milliamps. And if you take that times your 426, it's idling a little bit hot. It's running at 20 watts right now. So that's a little bit hot, but these 5881s are very tough tubes, and that's perfectly okay. It'll work fine. And if you look here, our filament string is sitting right at 36.1 volts. So there's your 0.1. Okay. So everything is good. And you'll see this thing will settle a little bit as it sits for a while. Everything will settle in, and the bias will actually drop a tiny little bit. But it'll just sit there and hold like that, and we don't get any red plating after long periods of time. If we did need to reduce that even more, we could adjust the value of this resistor. This resistor is actually going to control the idle current of the circuit. So if I lower this resistance a little bit, this may drop a tiny little bit, and your bias will go up, or I will go down. Your bias voltage will go down, I should say, which will make the tube run hotter. And if I make this resistor higher resistance, it'll do just the opposite. It'll drop our idle current even more. So that seems to be a pretty good compromise. The tubes don't run overly hot. They don't red plate or anything like that. And that's a pretty safe place for these to be right now. And I guess the proof is in the pudding. Let's see if we can put up some music and listen to it real quick. But first, this thing's hooked up to a speaker. Let me remove my microphone. And you can hear, I'm right against the speaker. I mean, tweeter, woofer, nothing. It is the quietest vacuum tube amplifier, for this age of an amp. This is the quietest amp I've ever heard. Or not heard, I should say. All right, let's put some music on. Okay, I'm just going to use the lapel microphone, so don't expect any great sound quality, but give you an idea of how it plays. Let's cue something up from the YouTube library. So there you go. Not too bad. And again, this is a lapel microphone, so I don't know what the audio quality is on it. Not too good, I would imagine. But at least you get to hear some sound. And, well, I think I'm going to do a separate video on checking the performance of the amplifier, because this video is probably epically long. I don't know. I've done a lot of footage. I got to go through everything and find out what's worth posting and what isn't, and get it edited. And then we'll do a separate video on the actual testing of the audio of the amplifier. We'll get it all put together and test it out. So again, as always, I wish you all peace, joy, happiness, and good health in your lives. And I look forward to seeing you again in the next video. And until then, stay well, and we'll see you soon. Bye-bye.